Welcome to the first video lecture on business calculus. I'm your instructor, Matthew Burkemper. Before we get into any mathematics in this first video, I want to kind of go over a little bit about how the course is going to work, since we are going to be mostly online for this semester. I will be periodically producing videos every couple of days over the course of a week, and each week you will be given an assignment in WebAssign based off of the lectures that I give you during that week. I have noticed from doing online lectures in the last few classes that we've had to do over this kind of stressful year that a lot of people will wait until the assignment is due before they watch all the lectures from that week and then do the assignment. That kind of strategy is kind of detrimental to your ability to actually learn the material. You can't really learn an entire week's worth of material in one sitting. I encourage you instead space out watching the videos. You don't have to watch them exactly when I post them, but space it out a little bit. And really you want to take advantage of the fact that I am doing video lectures and use that to be able to re-watch parts of videos that you have struggled with the first time through. Then you can start the homework before it's due, because I'll give you plenty of time to work on that homework before you actually have to have it complete. I'll also make sure to have my office hours available for you to ask questions between when I assign the homework and before it is due. So a typical week would look something like, so yeah. So right there, it's the week. I'll probably be posting videos on Monday, Wednesday, and Friday. Gonna try to keep to a three sections a week. So some weeks we'll actually have 4 lectures instead. I'll try to figure out exactly when I'm going to post those for there, but typically it'll be 3. I'll assign homework on Friday. And then that will be due the following Wednesday. Usually around midnight. Or, yeah, I'm going to stick with midnight for when the homework is due. So you'll have all the way from Friday, or if I post it a little early, maybe a little earlier than that, and then it'll be due at midnight on Wednesday. My office hours will be on Monday and Wednesday. I currently plan to have those at 12:30, and so there'll be 2 office hours that you can visit every time before the homework is actually due. So for your own sake, for your ability to actually learn the material and absorb the material, take advantage of this opportunity instead of falling into that procrastination trap that is so easy to get into. But alright, let's move on to the mathematics. In this class, we are going to be working on chapters 1 through 6 of our book, the Calculus and Applied Approach, 10th edition. Pretty much we'll be covering all the material from those chapters, and the first 2/3 of our first chapter, chapter 1, is mostly just going to be a review of topics from college algebra. But I do want to make sure that we go through these so we are reminded of the facts that are going to be important throughout all of calculus. These are not the only algebra facts that we will use throughout the course, but these are the core ones that we'll be using very frequently. In section 1.1, we're going to start talking about the Cartesian plane. Basically, a lot of the important tools in calculus start from a very geometrical idea. And we're going to look at the two-dimensional plane throughout the entire course. Moving up to 3 dimensions is the realm of Calc 3, so we won't really be talking about that. Though this book does, because this book is supposed to be somewhat comprehensive. I think in chapter 7, yeah, chapter 7, they get into a little bit of that. If you are curious about how that kind of stuff can work. Of course, you might want to wait until we've gone through the two-dimensional stuff, because that will actually build up into the the multivariable function calculus that they cover in section 7. In order to work with the plane, we need to introduce a coordinate system. And while we could draw this by hand, since we're working with a computer, we can frequently switch to using a program for graphing to speed it up. This is specifically a program called GeoGebra. It's up there in the title. This is a graphing program that I recommend to just about anybody that is doing anything with graphing. You can search for it online. It's really easy to find. There's also even a phone app version that I use as well. So be prepared to see me using this in videos a lot, because it is very convenient to be able to graph using the computer. So our coordinate system, how our coordinates work, is we have these two perpendicular lines, and we label those lines based off a distance from the intersection point, with one side being positive numbers and the other side being negative numbers. So basically these are negatives of the distance from the intersection point. And we do the same thing on the vertical one. The horizontal line is going to be referred to as our x-axis. Let me go ahead and even put that in here. So this is our x-axis. Our vertical line is our y-axis. The place where they intersect, so that's this point here. And they called it A. The GeoGebra likes to name things as we go, but I'm just going to go ahead and rename that to its proper name of the origin. That is the intersection point of our two axes. These axes will divide space up into 4 parts. We call those parts quadrants. So we have quadrant up here, quadrant here, and so on and so forth. Usually those are labeled in a counterclockwise fashion, starting with the quadrant over here. We'll label those numerically, but we use Roman numerals traditionally. Oops, I don't want to rename that. So this is quadrant 1. Then we move counterclockwise, so this is quadrant 2. Quadrant 3. And quadrant 4. Now, we're not going to be too concerned with quadrants in this course. If you do anything with trigonometry, the particular quadrants become quite important. But one of the differences between the regular Calc 1 and this business calculus class is that we are not going to be working with any sort of trigonometry. So exactly what quadrants we're working with isn't going to be quite as important. And most of the time we're going to be more concerned with stuff in the first quadrant, because that's where everything is positive. But we can't ignore the rest of the plane, of course. Now, what are the coordinates? What does it mean to have coordinates? Well, we're going to label points on the plane using pairs of numbers, ordered pairs. So if we take a point like 8, 5, they go ahead and plot it for us and label it A. These numbers, 8 and 5, correspond to lengths along the x and y axes. So if we actually go ahead and drop perpendicular lines from this point A to our axes, you're supposed to put a perpendicular line there. There we go. Dropping a perpendicular line from A to the x-axis, we notice here that it hits that axis at the number 8. That is the first coordinate of the point A. It's the first number in our pair. That's telling us that to get to A from the origin, we had to go 8 distance horizontally. Same thing with our second coordinate of 5, that's our y coordinate. We have to go 5 up. Whether we go 5 up along the y-axis and then over, or if we go over and then 5 up to A, just parallel to the y-axis. So these are our x and y coordinates for our point, because those correspond to distances along the x and y axes. In this way, we are able to give a pair of number to every single point in the plane. And it's important also that these numbers are unique. Every point in the plane corresponds to exactly one pair of numbers. So if I pick a point, it'll have a unique pair of numbers for it. If I have a pair of numbers, it'll be some point out there in the plane. We call this system Cartesian Coordinates, named after a mathematician René Descartes. We also refer to these as rectangular coordinates because you can see how dropping these perpendiculars to our axes forms a nice rectangle. This actually is contrasted. If our axes were not perpendicular, we might have something that we call oblique coordinates, where we don't actually get an actual rectangle. We wouldn't have right angles. But this is by far the most commonly used coordinate system. So we just won't really worry about any of the other ones. The only other one that is almost as useful as this one is called polar coordinates, but until you get into some trigonometry, that's not really too easy to get into. So this is all we're going to be worrying about in this course. Let's go ahead and plot a few more points. I'm going to take these from problem 5. So in problem 5, they give us the 2 points of -3, 7 and 1, -1. They actually ask us to do a few things, but we'll only be working on part A for now. It says in exercises 3 through 12, A, plot the points. So we want to plot these 2 points. And I'm going to go ahead and do this by hand. So I first draw my axes. Note that I do put arrows on my axes. You don't necessarily need to do that. But one thing that a lot of people think they need to do that is put arrows on both sides of the axes. That's not actually what you want to be doing. The arrow doesn't just say that the line is going on to infinity, as some people think it does, but instead it's telling us what direction is the positive direction. So here, by putting an arrow on the right side of my horizontal line, I'm saying that the positive x values are on this side of the origin, while the negative x values are on the other side. Same thing here, the arrow goes on top of the y-axis because the top, these are all the positive y values versus the negative y values when I'm going down. So if I'm plotting the point -3, 7, that means I'm first going to travel a distance of 3 to the left. That's what the minus sign here means. So I'm going to move 3 over because we're going at the 7 on the y. I want to make sure I don't go too far out. Let's say that's about 3 there. So that's to the left of the origin, so it's a -3. So I move over to that -3. Next we need to go 7 parallel to the y-axis, and because this is a positive, we're going up. So if 7 is maybe around here on the y-axis, we go 3 over to the left, and 7 up to get the point negative 3, 7. For our other point, 1, negative 1, we're instead going a positive 1 distance to the right. So let's say that's about 1 there, and then we're going 1 down because we have a negative 1 here. So let's say negative 1 is right here. This is our point 1, negative 1. So that's simple enough, and it's something that we'll be doing pretty frequently. I won't even go through all these steps of actually finding it every time. We just want to kind of make this more natural and just kind of work with it really easily. If we want, we can also plot those in GeoGebra. So all I have to do here is I just go ahead and type in parentheses, and it actually even puts the closed parentheses in there for me. I have negative 3, 7 as my first point. It calls it A because it always names them as we go. Then I have 1, negative 1 as my second point, and it calls that one B. And notice it's very similar to what I just drew. Though it's nice to be able to use technology to plot them for us. It's also pretty useful to be able to draw it by hand as well, because there's limits to what we can do with GeoGebra. Now, if we continue reading the directions for this problem, in part B, they want us to find the distance between the 2 points. So how do we find the distance between those 2 points? Well, first we need to be able to do some basic geometry. How do we find the distance between 2 points? Well, what we're going to do is fall back on what we call the Pythagorean theorem, which you probably have seen before. Hopefully you have. Recall that what the Pythagorean theorem says is if we have a right triangle, so we have a right angle here, we'll label this triangle with side lengths of A and B and a hypotenuse of C. Pythagorean theorem says as long as we have these as side lengths of a right triangle, as we have them here, they have to satisfy the equation that a squared plus b squared needs to equal c squared. Now, how is this helpful to us here? Well, we can go ahead and, taking those 2 points, we can make a vertical line through one of the points and a horizontal line through the other point. So let's say I go ahead and make a vertical line through A. So I'm just basically dropping a perpendicular down to the x-axis to do that. I also make a horizontal line through B by just making a perpendicular to the y-axis. If I then make a segment from A to B, I have a right triangle. The horizontal line and the vertical line are automatically perpendicular to each other. So I can use the fact that we have a right triangle here in order to use the Pythagorean theorem. I know that the length of the hypotenuse here, which they've actually called h, is equal, or well, the square of that is equal to the sum of the squares of the 2 sides of our triangle. But because these are horizontal and vertical, we can actually just go ahead and subtract x values and y values to make those actually work. So say here, along our horizontal, we use our x value of 1 for B and our x value of negative 3 for A. That's actually going to still be true for our intersection point down here. It's still going to have an x value of negative 3 because everything along this vertical line has x values of negative 3. And then the difference between 1 and negative 3 is this length. It's a length of 4. Same thing here. Our y value of 7 for our point A versus our y value of negative 1 for everything along this horizontal line. That means that we have a total distance along this vertical line of 8. And we can use those 2 facts in order to find the length of our hypotenuse. Though let's actually write this out. We end up getting a formula for the distance between 2 points, called the distance formula. So if we have 2 points, and here we're going to go ahead and use variables x1, y1, and x2, y2. If we have those 2 points, so that the distance squared is going to equal the sum of the distances along our horizontal and vertical lines. I'm going to go ahead and move that square over as a square root. So we have that the distance is the square root of the difference between our x's squared plus the difference between our y's squared. And we don't really have to worry about whether or not x1 is bigger than x2 or if y1 is bigger than y2 because the square gets rid of any negatives. That will just take care of itself. So really, when we're taking these differences, generally we'll just use the bigger one and not worry about keeping the same order here. It's not actually going to be the same when we get to slope later on. There we do have to pay attention to the order more. Here we don't have to pay attention to that at all. So when it comes to these points here, the negative 3, 7, and the 1, negative 1, we want to find that length there. We're going to take the difference between our x values. So we have a negative 3 and a 1. I'm going to go ahead and take 1 minus that negative 3. So we do need to end up adding 1 and 3 together. That's going to be squared. Then we're going to have our difference between our y values. I'm going to go ahead and pick the 7 first this time, just because the bigger number. So 7 minus the negative 1. So we have a 4 squared plus an 8 squared. I need another parentheses there. We can go ahead and use a calculator to find out what 4 squared plus 8 squared is. It turns out that what we have here is a square root of 80, which if you want, we can go ahead and approximate to be, what was it, 8.94. And in fact, we've already seen this number if you've been paying attention. So when I put the segment here from A to B, GeoGebra automatically calculated its length as 8.94. So GeoGebra will give those numbers to you if you put in segments like I did here using the segment tool. But it is kind of important here that we have an exact answer. The answer really isn't 8.94. That's an approximation. The answer here is square root of 80. And especially in our online homework, the square root of 80 is what they're generally going to be expecting. They want that exact answer. If we just put in 8.94, it probably will not recognize that as the correct answer. It'll give you an error, and it probably won't even tell you why you're wrong, because it's looking for that exact answer. If you do want to put in a little extra work, you can pull out any squares that are in there. You can actually, because 80 is 16 times 5, we can write that as a 4 times the square root of 5. WebAssign will recognize both of those as correct. So either one of these can be our answer. In fact, leaving it as square root of 80 will generally be good enough, unless there's some cancellation that you can do. But that's not going to be true when we're just doing distance formula problems. So make sure you know how to use the distance formula. It will give you the exact answers, even when GeoGebra approximates those answers. Now, if it does come out to be an integer, then you kind of get lucky. It'll be fine. You don't have to worry about it then. But you shouldn't count on that. It's not always going to be the case. Alright, there's one more part to this problem that we want to talk about. Part C, find the midpoint of the line segment joining the points. So if we have 2 points, they're connected by a line, there is a point that's right in the middle. Geometrically, what we're saying here is that the midpoint between 2 points is the point on the line segment connecting those points that is at an equal distance to those points. So we want to say this distance here and this distance here are equal to each other. Now, if we want to use this definition to find the coordinates of the point, that can get a little messy, but unfortunately there's a simple guess that we can make that will turn out to give us the correct answer. So let's actually first look at a number line. So basically, we're instead of working with a two-dimensional plane, we're working with a one-dimensional line. If we have two numbers on that line, let's say we have an A and a B, what is going to be the midpoint between these 2 points? If we think about it, all we're really talking about is the average between those 2 points. Right here in the middle, halfway between A and B, is the point, or the number, A plus B divided by 2. That is definitely halfway between A and B. And you can even calculate the distance between A and that. So if we look at, so the distances along the number line, you just take differences between the bigger number minus the smaller number. So we can say between A and A plus B over 2, we have A plus B over 2 minus A. That's just going to be if we simplify that, we can make that into a B minus A over 2. Between A plus B over 2 and B, we have B minus A plus B over 2. And if you simplify that one as well, you still get B minus A over 2. Those distances are equal to each other. And we just get that by taking the average. Well, it turns out in 2 dimensions, when we're working in Cartesian coordinates, we do exactly the same thing. All we need to do is average the x values and average the y values. And we get what we call the midpoint formula. So the midpoint between x1, y1 and x2, y2 is the point where the first coordinate is x1 plus x2 divided by 2, and the second component is y1 plus y2 over 2. We just take the averages between our x values and the averages of our y values. And it's just that simple. So here, our midpoint is the point where we take our negative 3 and 1, add those together and divide by 2. We have our 7 and our negative 1. We add those together, or subtract 1 from 7. Same thing. We divide by 2. Negative 3 plus 1, that's going to be a negative 2. 7 minus 1 is a 6. And then finally, negative 2 divided by 2 is a negative 1. 6 divided by 2 is a 3. Basically, the number halfway between negative 3 and 1 is a negative 1. So we have a negative 1 here. Halfway between 7 and negative 1 is a 3. We get this point, negative 1, 3. We can even go ahead and put those in here. If we plot the point negative 1, 3, we have a point C plotted halfway between A and B. In fact, GeoGebra does have a midpoint tool, which you can calculate the midpoint between those 2 points. It turns out to be exactly negative 1, 3, as we just found. So If we want to verify that everything is working correctly, we can go ahead and just make the line segments between A and C and from C to B. It'll calculate the distances for us. We could do that by hand, but because we kind of want to take it, we don't really want to go through all that work to do it in this particular problem. But we get 4.47 for both those distances. And so that this really is the midpoint between those 2 points. It's really just that simple. So those are the main tools that we want to take away from this section. We'll be adding more onto this as we go forward. In the next section, we'll actually be talking about using formulas between x values and y values and graphing the curves that are actually generated by those. But for now, that's really all we need to work with. We have these basic geometrical formulas, and now we can actually use them for applications. Let's actually work one of the problems. Let's work on problem 17. In problem 17, they give us 3 different points. They give us the points 0, 1, 3, 7, and 4, negative 1. These 3 points can be the vertices of a triangle. And the book is claiming that we actually have a right triangle. But they want us to make sure that that's actually true. Let's go ahead and actually plot those points. So 0, 1, this is a point on the y-axis, because the 0 here means that we didn't go any horizontal. So we have a point A here on the x-axis. Our next point is a 3, 7. This is a point in our first quadrant because we have both positive numbers here. Then our third point is 4, negative 1. This one's down here in the fourth quadrant. So we have 3 different points. And they might look like they form a right triangle. We'll go ahead and actually maybe connect those points so we can actually make that a little bit clearer. Let's actually move that name over there. If you look at that, you might say, well, that does look like a right triangle. Specifically here at A, it looks like we do have a right angle. But how can we be sure? Well, the key point here is that to determine whether something is a right triangle, we can always use the Pythagorean theorem. Not only do the side lengths of a right triangle satisfy the Pythagorean theorem formula, but any triangle that does satisfy that formula has to also be a right triangle. So we'll go ahead and calculate the lengths of the sides of this triangle. So let's say the distance between, let's just basically find the distance between every pair of points. So we'll say the distance, I'll just abbreviate that as D, between 0, 1 and 3, 7. Remember, the distance formula has us take a square root. Then we take the difference between our x values. Our x values here are 0 and 3. I don't have to worry about which order I do those in, so I'll go ahead and pick the 3 first. So 3 minus 0 squared. Obviously, the 0 doesn't really do much there, but I'm going to put it there just so we're clear about what we're doing. Then we have a difference between our y values. We have a 1 and a 7. So since 7 is bigger, I'll put that first. 7 minus 1. So we have 3 squared plus a 6 squared. We can go ahead and use a calculator to actually work that out what that is. But we end up getting a square root of 45. And if you care, we can actually go ahead and simplify that down to 3 times the square root of 5 because we can pull a 9 out of the 45. But I'm not going to really require that here. It actually doesn't help us to do that. The square root of 45 is actually kind of the important number that we want. If we could move on, the distance between our first point, 0, 1, and our third point, 4, negative 1, we do exactly the same kind of thing. We have a square root. We take our difference between our x values. We have a 0 and a 4. So we have 4 minus 0 squared. Then we have a 1 and a negative 1 for our y values. Again, since the order doesn't matter, I'll go ahead and pick the 1 minus the negative 1, which actually just becomes a 1 plus 1. So we end up getting a 4 squared and a 2 squared. When we add those together, we get a 20. So we have a square root of 20. And actually, this one can be simplified as well if you prefer. You can pull a 4 out of the 20, and that will leave us with a 2 square root of 5. Our last one, now we're taking the distance between our second and third points. We have 3, 7, and 4, negative 1. And the process is still the same. We have our y values of 3 and 4, so I'll go ahead and subtract those, picking 4 first just because it's the bigger one. So 4 minus 3 squared. Now our y values are 7 and negative 1. Again, I'm going to take 7 minus the negative 1, which just really means 7 plus 1. So here we have a 1 squared plus an 8 squared. And so we end up getting a square root of 65. This one actually can't be simplified like the other two were. But the main thing here is that if we were to square these side lengths, we get 45, 20, and 65. Well, since 45 plus 20 does equal 65, that means the square of the side lengths do in fact add up to be the square of the hypotenuse. And say this is, our a is square root of 45, so square root of 45 squared plus the square root of 20 squared is the same thing as the square root of 65 squared. And in fact, so that's why leaving it as just a single square root can be helpful when you're doing these kind of problems. Because otherwise we would actually have to square 3 times square root of 5, and that's a little bit messy, but you did more work to get to 3 times square root of 5. You might as well just have left it as square root of 45. But the point here is we do actually satisfy the Pythagorean theorem. The sum of the squares of our two sides is equal to the square of the hypotenuse. And so this triangle here is in fact a right triangle. Alright, so that's all I'm going to cover for now. Again, we'll move into working with formulas, working with the graphs of various equations in the next section. But for now, we just want to make sure that we do know how the Cartesian coordinates work. I'm sure you guys have seen them before, but we're going to be using them quite often in this course throughout calculus, and we want to make sure that we do know what we're doing. So I'll see you guys in our next video.